Hello friends, today I will discuss about overfluxing relay for transformer. Before going through this video, you are requested to please go through my channel and do subscribe my channel if not subscribed earlier, and also press bell button for notification of videos to be uploaded in future. Transformer overflux protection is provided to protect the transformer core from overfluxing. As per law of the transformation, that is induced EMF in any winding is given by V equal to root over of 2 into pi into F into N into phi, where F is the frequency of the supply voltage and N is the number of turn of the winding and phi is the flux in the core. So flux phi is equal to V by root over of 2 into pi into F into N. Now number of turn of any winding is constant, therefore the flux is proportional to the supply voltage and inversely proportional to the frequency of the supply. A core loss of the transformer is comprises of two types of losses. One is hysteresis losses and another is eddy current losses. Hysteresis losses is given by the WH is equal to K and B max to the power 1.6 F into V in watts, where Kn is the coefficient of eddy current losses and B max is the maximum value of the flux density in Weber per meter square, and F is the supply frequency in Hertz, and B is the volume of the magnetic material in meter cube. And eddy current losses is given by WE is equal to Ke into B max to the power square into frequency square into T square into B, where Ke is the coefficient of the eddy current losses and B max is the maximum value of the flux density in the core in Weber per meter square, and F is the supply frequency in Hertz, and T is the thickness of lamination in the meter, and B is the volume of the magnetic material in meter cube. So we can see that both the hysteresis loss and eddy current loss is directly dependent on the flux of the core. If the flux in the core increases, then hysteresis loss and eddy current loss will increase, and therefore it will result in heating of the transformer. Now what are the reasons that leads to the overfluxing of the transformer? Number one is the high system voltage. If system voltage increases, then it will result in the overflux in the core of the transformer. Number two is generator full load rejection. Number three is increase in voltage due to light loading of the transmission line, that is Franke effect. And number four is the low system frequency. As the flux is inversely proportional to the frequency of the system, if frequency is decreased, then flux in the core will increase. Now as per the law of the induced EMF of the transformer, V is equal to root over of 2 into pi into F into N into phi. So phi is proportional to the voltage of the system and inversely proportional to the frequency of the system. So how does the relay sense the voltage and frequency of the system? A PT secondary input supply, that is face-to-face supply of voltage 110 volt is given to the relay, either VRY or VYB, from which the voltage and frequency of the system can be sensed by the relay. Now as the BT secondary voltage at rated primary volt is 110 volt and rated frequency is 50 Hz, therefore the per unit value will be the rated secondary face-to-face voltage by rated frequency, that is 110 by 50, which is equal to 2.2. So a setting of 1.05 per unit would be equal to 110 by 50 into 1.05 is equal to 2.31. Time delayed IDMT characteristics is given by the overfluxing protection to detect the fault and trip after certain period of time. The IDMT characteristics for Minecam relay is given by, that is T equal to T is the trip time is equal to TMS divided by M minus 1 square, where m is equal to the ratio of b by f in measured quantity divided by the ratio of b by f by the setting quantity, where b and f are the measured quantity of the voltage and frequency of the system. Normally, the voltage B by F ratio for trip setting is given by 1.05 to 1.1 per unit. For different value of the TMS, that is 1, 2, 4 and 8 and 12, and for the same value of the M, that is the measured quantity of the voltage by frequency ratio to the by the setting given by the relay, the trip time will be differ for different value of the TMS as given by the 5 different characteristics. For same value of the TMS, that is TMS is equal to 1, the M, if M is equal to 1.05 and the value of the M is equal to 1.15, the trip time will be lower. So the characteristics curve has been shown for different value of the M. As for the same TMS, the trip time will be differ. Now let us take an example. The value of the M is equal to 1.05 and TMS is taken as 1. Then trip time T is given by T equal to a TMS divided by M minus 1 square. That is T equal to 1 by 1.05 minus 1 square, which comes as 400 second. Again, if the M is equal to 1.15, that is the measured quantity of the voltage per frequency is more compared to the earlier cases. Then for the same TMS, that is TMS is equal to 1, trip time will be equal to 44.44 second. Again, heavy BMEC type RATUB2 use following IDMT characteristics, that is given by trip time T equal to 0.8 plus 0.18 into K divided by M minus 1 square, where K is the TMS setting given by the relay, where M is the measured voltage by frequency ratio to the setting of the voltage by frequency ratio. So the different value of the K and for different value of the M, the characteristics is given by the following curve. Now consider the M is equal to 1.1 and K is equal to 1. Therefore the trip time T is equal to given by 0.8 plus 0.18 into TMS, that is 1 divided by 1.1 minus 1 whole square. So the trip time comes as 18.8 second. So the overfluxing relay characteristics use the IDMT characteristics, but these characteristics vary for different relay.